Section 4.9, Antiderivatives. This is our last section in Chapter 4, and this actually becomes our foundation for how we start Chapter 5 and actually the rest of this Calculus 1 course. We start first with a definition. A function capital F is called an antiderivative of lowercase f on an interval I if f prime of x is equal to lowercase f of x for all x in I. So for example, since the derivative with respect to x of x cubed is 3x squared, then we can say that capital F of x equal to x cubed is an antiderivative of lowercase f of x, which is equal to 3x squared. Because if you take the derivative of capital F of x, f prime of x is equal to 3x squared, which is lowercase f of x. However, it's quite easy to see that x cubed plus 40 is also an antiderivative because the derivative with respect to x of x cubed plus 40 would also be 3x squared, since the derivative of 40 is just 0. And so is x cubed plus any constant, for that matter. So what we're seeing here is that a function can have an infinite number of antiderivatives. A few sections ago, we had a concept that said if two derivatives are equal, lowercase f prime of x equal to lowercase g prime of x on an interval, then the function f minus g is constant, which means you could express lowercase f of x as g of x plus c for some constant. Combining that previously known fact with this new definition of antiderivatives, we get the following theorem. If capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of lowercase f on I is capital F of x, that's the antiderivative, plus some constant c. And we're just going to be using that constant, capital C, to stand for an arbitrary constant. So let's look at a few examples. We want to find the most general antiderivatives of the following. So part A, f of x equal sine x. So first of all, what we want to think of here is we're not taking the derivative of these functions in these examples. We want to think of the functions whose derivative is what we see in front of us. So we want to think, what is the function where if you take its derivative, you get sine x. So we might start with a guess that if we take the derivative of cosine x, that would give us sine x, but we actually know that if you take the derivative of cosine x, you get negative sine x. So, to help us adjust this, if we take the derivative with respect to x of negative cosine x, then that gives us positive sine x. So we would first say that capital F would be negative cosine of x. So capital F of x is negative cosine x. But then to answer the question fully, the most general antiderivative that would be that capital F function plus some arbitrary constant. So it would be negative cosine x plus capital C. So that's it. Just thinking of what that antiderivative is and then tacking on a constant to that. So part B. Here we're given that lowercase f of x is 1 over x. So again, we want to think of the function capital F of x, who, when you take the derivative of it, you get 1 over x. This goes back a few sections. There was actually a very specific example that we looked at where we saw that the derivative with respect to x of the natural log of the absolute value of x is what we want to use. The reason why we want to use that is with that absolute value, then you don't have to worry about x being positive or negative. This is always going to work out. So the most general antiderivative, the answer, that's going to be the natural log of the absolute value of x plus, again, an arbitrary constant, capital C. And it doesn't matter that we keep using capital C as the arbitrary constant. And then finally, part C of this example, here f of x is equal to x to the n, where n is not equal to -1. If you think about n being equal to -1, that means x to the -1 power, which means 1 over x. So part C is really just a follow-up to part B. So here we notice that we have a power. So we want to think of the derivative with respect to x of some capital F of x function that equals a power function. So this is a way of reversing the derivative process for a power function. So maybe to help us get a sense of this, let's think of, well, the derivative with respect to x of the one that we saw before, x cubed is equal to 3x squared. So if you want to think of, well, how could you get x squared? Then you can think, well, what I had with x cubed, I would have to just make sure that the 3 doesn't stick around in my answer. So if I divide by 3, the derivative of 1/3 x cubed, that would give us x squared. And we can use that as a guide to help us figure out the function whose derivative is x to the n. So the way that I like to think of this, you want to end up with x to the n. So you know that you have to have started with a power that was 1 more than n. That would be x to the n plus 1. But then you don't want that power n plus 1 to show up as a coefficient, so you need to divide by that. And that's it. The antiderivative, capital F of x, would be x to the n plus 1 divided by n plus 1. So then the most general antiderivative, the final answer, would again be just that function, x to the n plus 1 divided by n plus 1 plus an arbitrary constant. All right, one application of antiderivatives is with what is called a differential equation, which we've actually seen when we looked at the section on exponential functions. So we're going to look at two examples. First, find f of t if f prime of t is equal to t plus 1 over t to the third, where t is positive, and f of 1 is equal to 6. So first we're going to find the general antiderivative. Then we can use the given value f of 1 equals 6 to find that arbitrary constant c. So we're given that f prime of t is equal to t plus 1 over t cubed. And to actually use something that we saw above, I'm going to rewrite this as t plus t to the negative 3. So I can see that those are both power functions. So again, what we're saying is that the derivative with respect to t of some function is equal to t plus t to the negative 3. So we're thinking of that capital F of t would have been the previous notation, but here they're saying, well, let's just name that as our regular function notation. So we're trying to find out what f of t is. So f of t, since I have two power functions here, I can notice that the first one is t to the first power. So I have to increase that power by 1. So that would be t to the second power. That's what's meant by n plus 1, just adding 1 to the power. But then I have to divide by that new power. And then with the second piece of this, t to the negative 3, I again need to add 1 to the power. So that would be negative 3 plus 1 is negative 2. but then I have to divide by that new power. So antiderivatives with power functions increase the power by 1 and divide by the new power. You can see that this is pretty much the opposite of what we did with derivatives. And then finally, we need a general antiderivative. So this is where we get plus c. Now that we have that, we can use the given value f of 1 equal to 6 to find the constant. So we're going to find c. So we'll use f of 1 equals 6, which means plug in 1 for t, and then f of 1 is equal to 6. So we would have f of 1 on the left, and then 1 squared, which is 1 divided by 2, plus 1 to the negative 2 is still 1 divided by negative 2, and then plus c. We're given that f of 1 is 6, and 1/2 plus 1 over negative 2, that's the same thing as 1/2 minus 1/2, that's 0. And 0 plus c is c. So this tells us that our answer would be f of t equal to t squared over 2. And instead of writing plus t to the negative 2 over negative 2, I'm just going to write minus t to the negative 2 divided by 2. And then instead of writing c, I'm just going to write 6, since we know that it's equal to 6. So if you're wondering, well, how would I know if I got the right answer? You know how to take derivatives. Just from what I have here, f prime of t, the derivative of t squared over 2 would be 2 times t over 2, which would just simplify to t, and then minus negative 2 times t to the negative 3 over 2. Notice that the minus the negative turns into a positive, and the 2 over the 2 turns into a 1. And then the derivative of 6 is just 0, and that equals exactly what we started with when you go all the way back to t plus t to the negative 3. Okay, let's look at another example. Find a function f if the second derivative of f is equal to 12x squared plus 6 minus 4, and we're given two function values. F of 0 is 4, and f of 1 is 1. This is what's called a second order differential equation. You'll see more of these in Math 70, and then a couple semesters later in Math 84. So first of all, f prime of x is the antiderivative of the second derivative of f. And then f of x is the antiderivative of f prime of x. So we just really need to do an antiderivative and then do another antiderivative. So if the second derivative is 12x squared plus 6x minus 4, then the first derivative, using again the power rules that we were seeing before, I want to take x squared and increase the power, so that would be x to the 2 plus 1, which is 3, but then I need to divide by that new power, and then with 6 times x, that would be 6 times x to the second power, but then I have to divide by that power. With the constant, just think constants are the derivatives of linear functions. They're the slope. So this would have to be 4 times x. And again, just check. Does it make sense that the derivative of 4x is 4? Yes. So then the antiderivative of 4 goes back to 4x. And then we need our constant. Now we can't figure out c yet. We have to go on to f of x, and then we'll eventually be able to find our constants. So now f prime of x, we have it here. Maybe let's rewrite that in a simpler way. So this becomes 4x cubed plus 3x squared minus 4x plus c. And now let's find another antiderivative to get f of x. So f of x is equal to, this will be 4 times x to the, again, increase the power, but then divide by the new power, plus 3 times x squared, again, increase the power to x cubed, but divide by the new power, minus 4 times, instead of x to the first, it's now x to the second, but divide by the new power, plus c is a constant, and the antiderivative of a constant is just c times the independent variable, in this case x. And then I need another constant. And I don't want to use capital C, I need something to differentiate from it, so I'll say capital D. And then finally f of x, simplifying what we have, is x to the fourth plus x cubed minus 2x squared plus c times x plus d. And now we'll use the given values to find our constants. So first I'm going to use f of 0 equals 4. So I'll plug in 0 for x. And you can see that that's a pretty simple thing to do. I'm just going to be left with d. And since f of 0 was 4, it means that d is equal to 4. And then I'll also use that f of 1 is 1. So f of 1, that would be 1 to the fourth, which is 1, plus 1 to the third, which is 1, minus 2 times 1 squared, which is minus 2, plus c times 1 is c, and then plus d, but we already know that d is 4. And since f of 1 is equal to 1, and then on the right-hand side I have 2 minus 2, so they cancel, and then plus c plus 4. So subtracting 4, c is equal to negative 3. So then our answer for our function, f of x, equal to x to the fourth plus x cubed minus 2x squared minus 3 times x plus 4. And again, if you want to check the answer, take the derivative and then find the second derivative and see if you get all the way back to 12x squared plus 6x minus 4. All right, one final application of antiderivatives relates back to how position, velocity, and acceleration are related. We've seen before that for an object in motion, the acceleration function is the derivative of the velocity function, and the velocity function is the derivative of the position function. We can also put these all together and say this. Acceleration is the first derivative of velocity, and it's also the second derivative of position. So as an example, a ball is thrown upward with a speed of 48 feet per second from the edge of a building 432 feet above the ground. Find its height above the ground t seconds later. Also find when the ball reaches its maximum height and when the ball hits the ground. You will need to start with the fact that the acceleration due to gravity is negative 32 feet per second squared. It is negative because gravity pulls the ball down towards the ground. So as a little bit of an image with this, let's imagine that here's our building and that the height of that building, 432 feet. And then someone is standing on the edge of the building and they throw the ball up, but as we expect, it goes up and then reaches some highest point and then comes back down and hits the ground. So we know that we're going to expect to get some function for the height of the ball being above the ground t seconds later. That has to be a quadratic. And it has to have a negative leading coefficient because that quadratic is opening down. So we're starting with the fact that there's acceleration. So the acceleration that's acting on this ball at any point in time is always negative 32 feet per second squared. And I'll leave the units out of this because we understand that acceleration is going to be feet per second squared, velocity is going to be feet per second, and then position is going to be feet. So, since a of t is equal to negative 32, that means that v prime of t is equal to negative 32. And if we want to find the velocity function, we use the antiderivative. So v of t is the antiderivative of the acceleration function, which means that v of t would be the antiderivative of the constant negative 32, which has to be negative 32 times the independent variable, which in this case is time, or t, and then plus some general constant, we'll say again, capital C. So now at this point, we can actually figure out what C is by going back to what we were first given. The ball is thrown upward with a speed of 48 feet per second. This means at the very beginning, when time is equal to 0, it means that our initial velocity was 48. So initial velocity that means the velocity at time 0 is 48. So v of 0 would be negative 32 times 0 plus c, since v of 0 is 48 and negative 32 times 0 is 0, that means that our constant is 48. So our velocity function is actually v of t equal to negative 32t plus 48. So now we know acceleration, negative 32, that's a constant acceleration. We know velocity, it's not constant, it does change over time. So then to find the position function, s of t is the antiderivative of v of t. So then s of t, very similar to some previous examples. Again, we're using some power functions here. I'd have negative 32, the constant, and then t, it was t to the first, but now I raise the power to the second, but then I divide by that new power. Plus 48, that's a constant, so the antiderivative will be that constant times the independent variable, and then plus another arbitrary constant for this antiderivative, just like the last example. So then s of t is equal to negative 16 t squared plus 48t plus d. So then to find my constant, we're going to use another idea of an initial value. We'll have our initial position. The position of the ball at 0 seconds when it was first thrown is 432 feet. So the initial position, that would be s of 0. That's equal to 432 feet. So that means s of 0 is equal to negative 16 times 0 squared plus 48 times 0 plus d, and again, s of 0 is 432, so that's what d is equal to. So then the first question that we had was find its height above the ground t seconds later. So the height above the ground is now just our finished position function. So the height above the ground at any time t that would be s of t equal to negative 16t squared plus 48t plus 432. So now you can see how those quadratics actually come about. It starts with acceleration and then goes back to velocity, and then back to position. So now let's use this to answer the final couple of questions. So the next question that we had was, find when the ball reaches its maximum height. So there's a couple of ways that we can figure this out. So when does the ball reach the maximum height? We could think back to what we did in a previous section and find the extreme value of this function. That means take the derivative, find critical points. But let's also remember, when the ball reaches its maximum height, what's the velocity? It goes up, and then it turns around. The velocity is equal to 0. Notice that's the same thing as taking the first derivative of the position function, setting it equal to 0, and finding the critical point. So it's the same exact idea. So we already had our velocity function, negative 32t plus 48. So that means that t is equal to 48 over 32, which is the same thing as 3 over 2, or 1.5. And we're measuring time in seconds here. So 1.5 seconds. And then the other question that we had, when does the ball hit the ground? Just think it was thrown from the top of a building, and it goes up and then eventually hits the ground. But what's the height at the ground? Well, that's 0 feet. So when does the ball hit the ground? It's when the position function s of t is equal to 0. Which means negative 16t squared plus 48t plus 432, we set that equal to 0. So this just becomes a factoring problem. So we can factor out the negative 16, and I would have t squared minus 3t, and if you divide 432 by 16, you'll get 27. That means I can divide both sides by the negative 16 since it's just a constant. And I would have t squared minus 3t minus 27 equals 0. And then factoring, this gives me, let's see, two numbers that multiply to 27. So let's say negative 9 and positive 3. But when I add up negative 9 and 3, I get negative 6. So this doesn't work. So what do I do if I can't factor and find the value of t? I have to use the quadratic formula. T equal to negative b, so that'll be negative of negative 3, which is positive 3, plus or minus the square root of b squared is 9, minus 4 times 1 times negative 27, divided by 2. This gives me 3 plus or minus 9, and then plus 4 times 27 is 108, and then divided by 2. And then if you're wondering about your two answers there, let's just keep this in mind. One of them has plus a square root, so the square root of 9 plus 108, which is 117, divided by 2, and the other one is t equal to 3 minus the square root of 117 divided by 2. This one would be a negative amount of time, which has no actual realistic context, but it does relate to our picture. You could just think if you extended the left side of the parabola, that's what that really is meaning. So this one's not realistic, but we can get a final answer for t from the first one. So this is approximately 6.9 seconds. Just as a little note, if you see some other problems related to this, acceleration due to gravity, that's either what we started with, negative 32 feet per second squared. Again, maybe think of context. If you're considering down as being towards the Earth, that's why we're using negative. And if you're using the metric system, this would be 9.8, or I should say negative 9.8 meters per second squared. So just make a note of those in case you see some problems with these.